Hello, everybody. I want to welcome you all to EarthShift Global's webinar here today about LCA for emerging technologies. We're so very happy to welcome Mik Carbajales-Dale, who heads the Energy, Economy, Environment, or E3 Systems Analysis Group at Clemson University. His research focuses on the long-term, large-scale evolution and dynamics of the energy economy system, especially how development of energy resources affects social development and the effects of a future transition from fossil fuels to renewable energy technologies. Welcome, Mik.
Thanks very much for the introduction, Holly, and thank you so much for inviting me to talk with you all. I'm very happy to talk about the work that we're doing. So the motivation for this is essentially laid out in this kind of image here. So you can see we have TRL, which stands for Technology Readiness Levels. So that starts from kind of basic scientific concept at TRL1 right through to TRL9 when a technology is ready to be commercially developed. And so you can see traditional LCA coming down here from the left will probably get you to kind of, once you have a full-scale system or test system being operated at commercial scale, then you could do a traditional LCA. But as you can see over here, typically, or more and more often, funding agencies, so like the US Department of Energy, are asking us to do life cycle assessment or some kind of environmental assessment, even when the technology is kind of at the bench or just out of the lab scale at the bench scale. And so we're kind of working through, well, what does life cycle assessment even look like when you're trying to do it at such a kind of in an uncertain domain? Okay, so hopefully you are all familiar with the life cycle assessment framework as kind of outlined by the International Standards Organization. So the way that we kind of organize our work is through that framework. So we think in terms of what are the issues of dealing with emerging technologies through goal and scope, through inventory analysis, through impact assessment, and then interpretation. So typically when you're thinking about what I'm going to keep calling traditional LCA, you're thinking about comparison between alternative products, processes, or systems. You're looking for those environmental hotspots. You're supplying information for public policy. And there's, as I'm saying, we're increasingly being asked to think about guiding new product development, which is somewhat easier than kind of guiding technology development. So again, I'm going to kind of reiterate, LCA is traditionally done ex post. So when a product is already commercially available, you have a product and a process that you can kind of hold in your hands. You know what the production process looks like. You can go out and take measurements on that process. You can look at the energy inputs, the other material inputs, all those nice things that we like to track during inventory analysis. But we are increasingly seeing lots of ex-ante approaches to LCA. So basically before that product is commercially available. So there's not necessarily something you can hold in your hands or a process that you can go and study. And there's different flavors of that, this ex-ante approach. So prospective LCA is looking at emerging technologies in early phases of development. Anticipatory LCA, so non-predictive and inclusive of uncertainty, so looking at extreme case scenarios of future environmental burdens. Consequential LCA, which you could do on an existing technology, but look at kind of how it might emerge or kind of evolve during its deployment. So looking at kind of market responses to that product deployment. And then dynamic LCA, thinking about how changes to either the background or foreground system might kind of evolve over time and over different development pathways. So kind of all of these things kind of come together when we're thinking about this emerging technologies. So again, part of the motivation for this is if we think about this kind of seesaw here, we've got the down at the bottom here, this product life cycle. So once a product has been developed and it's being manufactured, then what are the levers that we have to improve that environmental performance? Well, we can think about manufacturing improvements. So maybe lowering the temperature slightly that something happens at, or a lower pressure, all things to try and kind of improve the energy use of that thing. We can think about end-of-life improvements, maybe some slight tweaks that we can make to make this thing more recyclable, something like that. The next step up, we could think about, well, what if we were to redesign that product, right? So then we can think about, well, there's different concepts or different ways that we might kind of structure that product. So design and architecture choices, we could choose different materials. What if we switch from this type of plastic to this type of plastic, or switch from steel to aluminum? Things where you're not fundamentally changing the kind of nature of that product. And then most fundamental stage, we can think about technology development and what kind of levers that we can pull there. And basically the idea is that once you have a technology that's kind of got to commercialization, then a lot of the environmental impacts are kind of baked into that system. And your opportunity to have kind of this leverage on that environmental performance is very much reduced. And so this is the kind of motivation for why Department of Energy or other people are trying to drive deeper into this technology development process and anticipate what the likely environmental impacts might be and how we could improve that performance. So as I said earlier, the way that we tend to think about this emerging technology pathway is through this idea of technology readiness levels. So this indicates the maturity, technological maturity of a given technology. So this was first developed by NASA in the 60s. For their purposes, it was going from kind of basic fundamental scientific principle up to launch readiness. Here, launch is going to mean, I mean, they were meaning literal launches. Here, we're thinking more in terms of kind of launching a product into the market, right? So a first of a kind manufacturing plant or something similar. So the TRL-1 would be the basic principle as observed in science. So an example might be when we first noticed the photoelectric effect for photovoltaics, we then start to kind of formulate that concept and understand it scientifically through stages 2 and 3. We then take it kind of into the laboratory and work on it there, maybe have some bench scale mock-ups through 5. At TRL-6, we're kind of taking a prototype into a representative environment, so out of the lab and into something more like it might be operating in a real world setting. And then from 7, 8, 9, it's more kind of scaling up to get to something approaching what could be a commercially viable setup. So as I said at the start, we kind of go from TRL-1 up through TRL-9. And traditional LCA at this kind of full scale level, then you have a set of kind of material flows and energy flows that you could, in theory, run through an LCA model, right? You pretty much have your foreground inventory there, and then you can run this full scale traditional LCA. But as I said, we're being asked increasingly to extend this domain of LCA down into the lower TRLs. And so we want to try and leverage different mechanisms that we can do to achieve that. So leveraging things like techno-economic analysis or other types of process modeling, maybe using first principles to try and divine what are the kind of bounds of how efficient that system could be, or those kinds of things. Obviously, we're going to be leveraging data that technology developers are providing at the bench scale or whatever it might be. But just, yeah, any way that we can push these environmental analyses down through that TRL is going to be beneficial. So just to kind of reiterate then, the motivations for this, we're pretty sure that there's going to be larger benefits to the environmental performance of these technologies if we can get to these lower technology development stages and have a kind of guiding hand as we're going through that process in terms of these are things that you should try and avoid. These are things you might want to try and achieve. Maybe here are some benchmarks, performance benchmarks that you can try and hit. As I said earlier, existing LCA guidelines, I think were probably pretty much written with the idea that you were going to be looking at existing products, and the kind of language that's used is typically kind of go and take some measurements in this factory over here kind of thing. And so obviously that needs some adjustment for thinking about emerging technologies. That's one way that we can think about emerging technologies. So thinking about technological maturity. And so here on this, this plot here, that's what's kind of plotted on this vertical axis. Another way that we often talk about emerging technologies, so something like, let's say, solar PV is an emerging technology because it hasn't been deployed. It's kind of makes up small percentages of most electric grids. And so that's something that we would call, or we called in this paper here, market maturity. And so then you can think about the interplay of these two maturity levels, so technological maturity and market maturity, and kind of divide this space up into these four quadrants. And so I'm going to talk about this up in this top quadrant. We're thinking about just another iteration of an existing technology in an existing market. So you might think something like the next generation of light-duty internal combustion engines in a developed, like in the US market. So the next design of, I don't know, the Ford F-150, something like that. Then as you're coming down to kind of still high technology maturity, but low market maturity, you could think about a redesign of a vehicle, light-duty internal combustion engine vehicle, but in a developing market. So I don't know, sub-Saharan Africa or something like that. And think about, well, how might that impact the LCA that you might do? Coming down here, we can think about high market maturity versus low technology maturity. And so that might be something like drop-in fuels for vehicles in the US market. So maybe renewable diesel that's going to be just a drop-in fuel that can be used in existing cars and existing fueling infrastructure. And then on the other end of the scale so we're thinking about low technology maturity, low market maturity would be something like Hyperloop. So a completely new transport service infrastructure system, right? Completely new technology. We don't know what it might look like. We don't know what it might be used for. There's some kind of basic schematic, some kind of slight testing is being done, but if it were deployed, we don't know what the use case, what the application might be at scale. So that's just another kind of sense of emerging that you could think of for emerging technologies. For most of the rest of the talk, I'm going to be talking about this technology maturity, so that technology readiness level, TRL. Okay, so some of the main methodological challenges that we have that come up for LCA of emerging technologies, and this is from a review of the literature that we've done, is comparability. So this is obviously an issue that comes up in LCA anyway, but here it's slightly different because it's not just comparability between studies, but comparability within your study. So because we don't know what the function of this technology might be once it's commercialized, what's going to be an appropriate functional unit to use? What's going to be an appropriate comparison, incumbent technology to compare against? The next issue is something like scale up. So we may have data available at the bench scale, but presumably we don't want to be thinking about the environmental impacts of this technology when it's at bench scale. We're thinking about what it's like once it's commercialized. So how are things like efficiency or processing, different processing systems that we might use, conversion systems, reactors? Are we using batch reactors? Are we using continuous reactors once we're at scale? So those kinds of issues, and trying to think about, are there certain kind of scaling laws that we can think as we go through that TRL process. Uncertainty, again, is obviously an issue in all types of LCA, but here we have very large bounds on both kind of parametric uncertainty, so in terms of kind of inventory inputs, but also kind of structural uncertainty as well regarding what sorts of processes there might be. Again, thinking about that functional unit issue. Data availability, clearly that's an issue in all LCA, but I mean, it's really difficult in this emerging space because, yeah, your data availability is just so much more reduced. And then assessment time, again, that's often an issue for most LCA. But here, what we're trying to do is kind of come up with these assessments in a timely manner to guide the development of this technology. So we need to be able to run these analyses quickly in order to kind of give feedback to the technology developers before they make their decision on to the next kind of TRL level. This is basically what we have right now is a group of us researchers have been working together for about 5 years in total now. And recently we've kind of become, I guess, formalized as part of a CTAC, so CTAC North America, so the Society of Environmental Toxicology and Chemistry, North America, and then ACLCA, American Center for Life Cycle Assessment, have these joint working groups. So they're on a whole bunch of different topics. So circularity, marine litter, and then Jewel Bergeson from the University of Calgary and I chair this LCA of Emerging Technologies work group. And we have a whole bunch of other folks that are involved with us from academia, from industry, from national labs, all folks that are kind of interested in this topic and thinking around ways to kind of advance the methodology to achieve that. Hopefully these slides are going to be made available, because I would very much encourage you to kind of click on these links here to see, to kind of come in contact with us. We are very much open to kind of bringing on new members. We want to try and be as open as possible and get as much input from different people as possible. So please come and join us. This is very much a kind of call to arms for us of trying to engage membership in this group. Okay, so the mission statement of that group is to improve the LCA of emerging technologies, so serve as a focal point for the identification, resolution, and communication of technical and methodological issues related to LCA of emerging technologies, and then facilitate, coordinate, and provide guidance for the development, implementation, and communication of LCA and its use. So the way that we're doing that is we kind of meet regularly and we work through kind of ways to advance the methodology. We then are putting together a website where we're going to kind of provide access to the kind of outputs that we're developing and try and elicit feedback, so comments on the products that we're producing in terms of white papers and the content on this website. We regularly hold special sessions, workshops at the main LCA and sustainability conferences. So ACLCA we attend each year. We're attending CTAC and then also CTAC North America, I should say, and then the ISSST conference as well. Okay, so that's kind of the background, and now to kind of dive into the specifics. So as I said, it's structured around the 4 stages of LCA. So the first one being goal and scope, of course. We're thinking about goal definition. What's the purpose of the LCA? Where in the technology cycle, development cycle is that technology? Are the uses and markets for the technology established and well developed? So as I said, We may know what this technology is going to be used for once it's developed. We might not know that, right? And then thinking about what questions is it reasonable to ask at which stage of that development cycle. And then 5 specific challenges, thinking about function, functional unit, foreground and background data, system boundary and uncertainty, comparison systems, and then critical review. So thinking through the goal, those are the questions which I already kind of went over. And then here is the kind of things that you might want to think about. So the way that we're thinking about this is kind of as a set of guidelines to go along with someone working through the ISO guidelines. So specific guidelines specific to people that are doing it for emerging technologies. So for the purpose of the LCA, is there a funding requirement? So from someone like DOE, do we have internal viability? Are we trying to achieve benchmarking, hotspot identification? Are the uses and markets for the technology established? So thinking about, is the use case obvious? So going back to that Hyperloop example, well, in some instances, people talk about Hyperloop as moving passengers. In other cases, it's talked about freight. In other terms, it's talked about as kind of a mixed use case, right? So, yeah, it's just difficult to know all the time. And then will that environmental impact depend on how it's used? Thinking about the development cycle, so this is obviously part of the key difference. We need to know what is the technology readiness level of the technology when we're assessing it. And then what is the level that we're talking about when we're kind of setting these environmental kind of benchmarks for? So we're talking about as a commercialized technology, as a kind of deployed technology. We're talking about first of a kind, nth of a kind, plant, that kind of stuff. And then thinking about what questions is it reasonable to ask at what stage in the process? I mean, clearly, we're going to struggle to get to ISO compliance at these early stages. So maybe we're thinking more about just screening or quick benchmark kind of ideas that we can pass back to developers. And then maybe we can say, well, maybe it's just too early to do an LCA. And maybe that's kind of the feedback. Look, we have too much uncertainty here. We need to kind of develop, and maybe we need to develop along a bunch of different pathways before we can start to kind of say whether one pathway is better than another pathway. And then thinking about how sensitivity and uncertainty can be used to inform rather than kind of mislead, right? And that's going to be reiterated in the interpretation too. So thinking about functional unit. So as I said, the function of this technology, once it's developed, might not be immediately apparent to us now, or it may change through that technology development process. So some intended uses may fail, and then the kind of technology developers may kind of go in a different direction for that. So since that's the case, then we're going to have to think about evaluating this system using a variety of potential functions and functional units. And since we're going to have to do that, then we may have to identify different incumbent technologies for those different functions and functional units. So just kind of do a suite of different comparisons. So if it's used in this way, then this would be the incumbent to compare. If it's used in this way, then this would be the incumbent comparison. And then clearly transparency is going to have to be key for all of this stuff. Thinking about consistent foreground and background data. So, so clearly we're thinking about, inherently in all of this is we're thinking about some time in the future when this technology is going to be commercialized, right? So depending on the level that it's at now, that may be 2-3 years in the future, it may be 10-20 years in the future. So clearly we need to be consistent in what we're assuming, obviously for the foreground system, but then also the background system. So something like how might the electricity grid evolve over the timeline, over the time horizon that we're talking about. And so an example here is hydrogen used as a, let's say, storage mechanism within the electric grid, often when people are doing that, they assume that that hydrogen is going to be generated using solar PV or wind or something like that, or low carbon electricity. Whereas if they compare it to a battery technology, they'll assume that the batteries are available now and they're using the storage, grid, they're storing grid electricity at the current mix. So clearly that's not a fair comparison, right? Okay, so clearly what we need to think about is being very explicit and transparent about that, how that background data is treated, and trying to work out how any changes that we've instigated are going to be propagated through that system. Then thinking about the inventory, so I'll say that the goal and scope and interpretation groups have done very much more work at this point than the inventory and impact assessment groups. So this inventory thing is going to be pretty brief. So the main challenges here, so we have a large data gaps, this issue of scale up. So how do we scale from, let's say, a bench scale system up to a fully commercial scale system? And then thinking about this blurring of attributional versus consequential. So it's kind of attributional in the sense that maybe the background system isn't going to change, but we're still doing this kind of consequential type amendment, modification of the inventory to take it from bench scale up to commercial scale. So in terms of data, we clearly need to articulate what the collection or estimation methods that we used were. Are we using kind of first principles? Did we take the bench scale data and do some modification of it? Are we using kind of learning curves, trend lines, that kind of thing? Okay, and so here, the way that we thought about it is kind of putting together these sample data documentation tables using a template, something like this, right? For the scaling, so as I said, basically we're thinking about, okay, we have data available when this technology is at bench scale. How are we going to think what that might mean when it's at commercial scale? And so there's a few different ways in which that could change, right? So one thing is just, let's say the size of a reactor is going to change from being a few, I don't know, maybe 100 milliliters at the bench scale to, I don't know, tens of thousands of liters at the commercial scale. So clearly those two reactors are going to have very different efficiencies, very different yields. But the actual type of reactor might change as well. So, or there may be a different type of processing that's done. And so there may be structural changes that need to be kind of implemented as we go up through that scale up process. And clearly something that's going to be useful here is using kind of process simulation software. So something like Aspen or SuperPro or something like that. It's going to be really helpful. Impact assessment, there's going to be a few issues that are particular to these emerging technologies. So something like new materials, if we're talking about development of new materials, they may not, like I'm thinking, I don't know, nanoparticles, right? We don't know the specific impacts of those materials when they're released into the environment. And so that becomes, an issue where maybe there's just whole kind of types of impacts that we're just blind to because we don't have them in our current LCIA methodologies. Other issues might be kind of classification. So we may have the inventory flows there, but there's new categories that need to be included, or there might be characterization issues because we're working in the future. Then the characterization may not be relevant to what we're talking about now, or there might be entirely new mechanisms just because there's a slight change to the type of material that's being released. And there, clearly, what we're trying to do is leverage the fact that we're connected with CTAC to try and engage people that are specifically involved in the development of these impact assessment models. Okay, and then finally, interpretation. So there's going to be a lot of information here, but one of the main challenges is the study limitation. So we have data quality issues. This attributional LCA may be insufficient because the technology may be very disruptive. So there we need to think about clear statements on data quality, being upfront about the scale, the TRL scale that we're at, doing some thinking about market maturity, and then also kind of doing some consequential LCA too. Completeness, we may need to rethink our notions of completeness here, because complete may not be feasible at all, right? So for an existent technology, then completeness means, did you collect all the data that was available, right? And to what extent did you? Whereas here we're talking about data that's literally not available, right? So, and we have a checklist to talk about that later. Consistency, clearly we're looking to the future, and so there's kind of questions that we could ask about what the state of the technology and background systems might be at that point in the future. So yeah, we need an explicit statement on the type of case being analyzed, and then working together with other people to try and develop a consistent set of future scenarios, maybe. So similar to the IPCC's pathways. Sensitivity and uncertainty, so this kind of echoes what we were talking about for goal and scope. We have high uncertainty, lots of potential sensitivity, and so really thinking through what those might mean, whether it's through kind of scenario, really robust scenario analysis, or other sensitivity methods. And then conclusions, recommendations, how might our recommendations change through that, the kind of TRL levels? Are there ways that we can kind of standardize some of the language around the conclusions, and then leveraging other tools, so MCDA. So yeah, completeness check, I mean, so what we're thinking is, rather than being kind of somewhat qualitative around this, yeah, thinking about how that's going to be linked to TRL as to whether or not that's kind of acceptable or not. Yeah, I'm going to skip over this. Different types of cases that we could think about. So for an incumbent technology that you're going to compare against, does it exist? Maybe you could think about comparing to the current average, current marginal, current best in class. And a lot of this comes from work that's being done in the carbon capture and use space. They're really thinking about life cycle assessment and what that means in that technology area. So for the emerging technology, the current status is your best guess of what it might look like once it's been commercialized, maybe an optimistic or a pessimistic case, or maybe you're thinking about bounding using first principles. And then thinking about near future versus distant future. So maybe not just at the commercialized stage, but kind of N of a kind plants into the future. And then, so that's both of those foreground systems, and then the background system. Are you going to model it with no change? Are you going to try and make some estimated guess as to what the background system might be doing through this time horizon? So for comparative conclusions, if we're doing monitoring or other policy, then we might want to just say the technology is better than the incumbent in the base case, is better than the incumbent only in an optimistic case, or likely to outperform the incumbent even under these kind of optimistic or outlier assumptions. Yeah, and a key point here, we're going to compare new technologies only on the same TRL if we're doing the monitoring there. Yeah, and we need to be very careful about how these low TRL assessments are going to be used to claim things like carbon neutrality or negativity, because clearly that could feed into policy planning in negative ways. So maybe we're thinking about recommendations, so go, no-go decisions for research and development, or for near-term deployment. And then hotspot conclusions, we were thinking maybe about kind of color scales, red, yellow, green. So being very kind of qualitative about the decision making, or thinking about maybe something like a bandwidth analysis that the Department of Energy has been doing recently in terms of potential to improve. How much leeway do we have in the potential improvement of this system? So in terms of kind of the language that could be used, we were borrowing, this is from the IPCC, again, from their kind of climate, the latest assessment report. So these are the kind of languages they're using. Kind of virtually certain would be 99 to 100% probability, or going through to exceptionally unlikely, 0 to 1% probability. So that kind of confidence language and trying to be precise about how that language is being used. Okay, and with that, we often run this type of presentation as a feed into a discussion session. So here are some of the questions that we tend to think about for those discussion sessions. But in general, so how prescriptive should these LCA guidelines be? And if we are prescriptive, what could be missed? How do we project performance into the future? And what does that mean for LCA or the inventory? For goal and scope, how can we best convey the uncertainty in early stage assessments? Should we be differentiating between just life cycle thinking, kind of generically, or kind of more quantitative LCA for early stage application? Inventory, when can and should we use proxy data versus collective data versus modeled or simulated data? And then how should that data be scaled through that technology development process? Impact assessment, do we need new midpoint impact categories? Are there ones that are kind of obviously missing right now, or ones that are obviously in need of updating? And then interpretation, what kinds of sensitivity or uncertainty analysis is appropriate in this case for emerging technologies? And then how can LCA practitioners who might not be expert in the background system evaluate consistency about background systems? So with that, I'll finish up and I'll turn it over to questions if anyone has any.
Thank you so much, Mik. There's so very much to consider, and that's why we have our Tom Etheridge, one of our senior sustainability advisors, here to ask questions, help monitor the audience's questions, and ask you. So thank you.
Thanks.
Thank you, Holly, and thank you, Mik, for a very interesting presentation on what's clearly a very hot topic right now, and it's nice to see it becoming more of a topic for discussion. I think it's something that's been important all along, and I think it's part of it shows a lot of where LCA has come in its maturity, and that we're now starting to talk about this more openly and try to understand it.
Yeah, sure. Thanks.
So one thing that you've harped on quite a bit, and I think is important, and we have a question from the audience that goes to it too, is around uncertainty and how you apply uncertainty. And that brings up a question first for me, though, is, in your opinion, is there a place where it's inappropriate to think about LCA? For example, is there a stage where it's so early in the product development that LCA really isn't relevant yet? Or what would do you have any comments there?
Yeah, and this is something that we talk about in our group all the time. And I think this is what this question around life cycle thinking versus LCA is trying to get at, is when we're thinking about LCA, we're thinking about the kind of quantitative analysis, and maybe that is really not very appropriate for very early stage technologies. So, for instance, DOE has these funding calls at Technology Readiness 3. Tell us what the carbon footprint of your process is or your product is right now. And okay, they're getting a number, but what does that number even mean? Right? Did someone just run some numbers on what they have right now? Did they assume something about the technology when it might be commercialized? Or how did they get to that assumption? I mean, it's almost picking a number out of a hat, you know. So I think there is, at that point, I think you have to go more into this kind of life cycle thinking. Well, these are the types of things. So does your process require high temperatures? Does your process require high pressures? I mean, is there high material throughput required? These kinds of things. Things that folks that do LCA on a day-to-day basis think about very clear or understand innately, I guess, because we're just steeped in that world, whereas someone on the technology development side they're just not even thinking about that kind of stuff, you know?
Exactly. It's almost a question of when does it go from being an educated guess to truly anticipatory LCA? What are you really trying to anticipate here?
Right, exactly.
And to follow on that, looking at your first question under interpretation, you talk about, you know, sensitivity and uncertainty, and, you know, which is better, perhaps, you know, probability distribution or best case, worst case scenarios. I can imagine good situations for both, and wonder if you've thought about that, or what you think of there, and what your guidance would be.
Yeah, it's really funny. So of all the topics that we discussed, we had a kind of initial workshop where the group got together in 2015, I think it was. And this specific question here caused a big hullabaloo, a big argument, because essentially some people were saying, well, if you have best case, worst case, then you can do a probability distribution by assuming a kind of uniform distribution between those two end cases. And some people were just like, no, you can't, right? You know the best case and you know the worst case, and that's the bounds, but you don't know what it looks like in between. So to try and kind of run that through a Monte Carlo with some other parameters in there and get some distribution is disingenuous, maybe. So yeah, I guess that comes back to what question are you trying to answer? Yeah, what's the purpose of this LCA? What are you trying to get at? So in some cases, a best case, worst case may be good enough. Mm-hmm. If you really need to do some sort of more kind of probabilistic analysis, then maybe you're going to have to go down that route. Yeah.
Ah, very interesting. And also, I think relates to one of the questions that we got from the audience. It says, can't we use the standard for eco-design that allows for uncertainty?
I think to a certain extent you can. And this is another question that's come up. I mean, in what sense is this not just good LCA, kind of a good implementation of the traditional LCA? And I think to a certain extent it is. It's just being more explicit about that. So I think making use of those tools that are already out there, so like eco-design, I think is entirely appropriate.
And we have another question that's more generally applicable to LCA, but I think it'd be particularly interesting to hear your thoughts on it from the standpoint of emerging technology. And it's, you know, how is LCA relevant for a company's sustainability reporting, like ESG, GRI, et cetera? And in particular, I think with emerging technologies, is it appropriate, or should it be appropriate for companies to talk about their potential impacts for their emerging technologies in their sustainability reports, or how that might affect some of these reporting guidelines and so forth?
Yeah, that's a really good question. I guess it would be, to what extent is there potential relying on a certain kind of scenario that they're assuming about the future potential of this new technology that they're developing? I mean, if it's relying on that very heavily, then clearly that conclusion is not robust, right? Under a different set of assumptions, then it would potentially collapse, right? Yeah, it's difficult to know how much of this would fundamentally change the kind of enterprise level, let's say, carbon footprint or some of those kind of indicators. Yeah, I don't know.
Yeah, I think it's a really good question. It's one that's going to be interesting to see how it evolves over the next few years.
Yeah, absolutely.
Well, with that, I want to thank you very much for your presentation, and it's a fascinating topic, and I'm sure it's going to be one that we're going to be hearing much more about at upcoming conferences. And anyway, thank you. And with that, I think I will end the webinar.
Thank you so much.